Okay, thank you. Let's start this tutorial session. I have 3 hours roughly to explain you a bit about quantum optimal transport from a, say, theoretical point of view. Okay, I'm most a theory guy. But then I show you in particular 2 approaches, one based on channels. So yesterday there was a question about what is actually a transport map and stuff in the quantum case. Well, this will partially answer. And then I'll move to another approach which is tailored for qubit systems, which is mostly tailored in principle with quantum computing applications, but there may be some extensions, some relevant aspects that are useful for other applications like many body systems and possibly quantum chemistry. Okay, so let's start really from scratch, because I saw yesterday we have a diverse background. Not everybody is familiar with quantum. Not everybody is familiar with classical optimal transport. So this hour, so I think at the very end, I will give one definition of quantum optimal transport based on the Gauss, Mouhot, Paul Cagliotti approach. But so forget a bit about quantum optimal transport for the moment. Let's focus only on quantum. Okay. So what do I mean by quantum system, which are slightly different than general non-commutative systems? Because, for example, yesterday we saw a talk, very nice talk on free probability, which is also non-classical, but is slightly different than quantum. I'll try to explain you a bit what is peculiar of quantum. So what are the basic tools in quantum systems? Okay, so again, this slide, which some people don't like, but I'll try to comment a bit more on this. Okay, so we try to make up a dictionary. If you are already familiar with the classical measure theory and you would like to translate these notions into notions in the quantum setting. Okay, so we try to build up a dictionary. And this is just a mathematical dictionary. So you start in measure theory with a set, which may be discrete, but also a measurable set. You have elements and you have subsets, measurable subsets if you're doing measure theory. And then on this set, you may define functions, okay, taking values in complex numbers. But okay, let's choose this for a moment as a notion of functions. And then functions may be bounded if the set is not finite, maybe also not necessarily bounded. But then you have also real valued functions as a very nice subclass. And non-negative, oops, sorry, this PSD should have gone to the other side of the table. So non-negative functions, okay? Now, if you have questions, we can also explain a bit more, okay? But just to tell you, these are classical concepts. Also, we have the concept of modulus squared of a complex valued functions at any point x. This is another function. Then once you have a function and a set, you see, you don't really need a measure in general. You can just do a summation over the points of the set. You get a series, which may converge or not. And then you have these small LP spaces, little LP spaces, which are just defined as usual. Okay, what are the quantum counterparts of these tools? We are building a non-commutative theory. So the basic thing is that our set becomes a structure, a space with a larger, so with a more precise structure, which is a Hilbert space. Okay. Now I'm going really to build a sort of a correspondence, but it's not really that all the elements of the Hilbert space are relevant. In some sense, only elements with the unit norm are relevant, because then you can rescale. All the operators, all the operations that we'll do, most of them will be linear. So in some sense, points in the space should correspond to vector. And also there is the standard quantum notation, which I believe is not used in free probability, right? I think something. The typical notation is that if you have an element on the Hilbert space, well, sometimes you write it this way if you are a mathematician, but if you are really doing quantum, you also write it with a cat notation if it belongs to H. Now this is quite useful, because then you can differentiate also the notation for the canonical element on the dual, right? So you have a bra notation, which is the linear functional, which acts by taking the scalar product with the psi. Okay, this is just the standard Dirac notation. But then, okay, these are elements, and what are the subsets, the relevant subsets? So you would like to have a sort of sigma algebra or a lattice of sets, and then you take instead the closed subspaces. If you are in infinite dimensions, you require also them to be closed, okay? Otherwise, you can think for simplicity that H is finite dimensional, okay? In my slides, I think I will only use finite dimensional spaces. Okay, now, what are functions? The non-commutative analog of functions in the quantum theory are operators. In general, if H is infinite dimensional, they may be unbounded, okay? But let's think, for example, in the bounded case, you have bounded operators with domain, which is the entire space H. D of A is, in general, a subset, a dense subset if it's unbounded, but you can think of it as a fully continuous defined on every element of H. Then real valued becomes self-adjoint operators. This is in some sense the correspondence of the value of a function is given by the eigenvalues okay, of the operators. And if you want to think about what are instead the corresponding of the level sets, well, the level set in some sense corresponds to the eigenspaces, okay? This is more or less the correspondence, right? And now if you want to, so non-negative operators are non-negative in the sense of operators, in the sense that the spectrum is non-negative or it is a positive semi-definite self-adjoint operator, okay? And another corresponding object that will appear sometimes is this, maybe I have a pointer, yes, this norm squared, which is simply the adjoint of A, which I denote with dagger or sometimes with star, times A, okay? So this gives you a non-negative self-adjoint operator. Now, what is the corresponding thing of summing over the values of a function? Well, if you have an operator, you want to sum the eigenvalues, you do the trace, okay? And finally, these small LP spaces become these spaces which I still denote with LP, but actually these are called the Schatten P spaces, okay, in general. Okay, now if it is finite dimensional and all the operators are bounded, now this is quite trivial as a condition, but just to tell you that you can build up a norm from this quantity. Okay, taking the pth root. Yeah.
Okay, I'm just wondering, so in general, as far as I know, like if A is a self-adjoint operator, its dagger is the same, right?
Yeah, right. So, but in general, okay, because if you don't have a self-adjoint, I don't know if maybe it will appear sometimes. So if A is not self-adjoint, you have this definition in general, okay?
Oh, yeah, so that's what I was asking. So this is like a general.
Yes, this is a general. Also here, if F is real valued or is already, yes, if it is a real valued, this is simply the squared, right? Otherwise, you take the adjoint. Yeah. Right, because in general, these are complex valued Hilbert spaces, right? Maybe something that I didn't mention. So you should think in terms of matrices, these are complex valued matrices, okay? Right, okay, so this is quite, so I'm doing this because I expected that somebody has never seen these notions, so maybe it's the first time I'm trying to do it quite slowly, okay? Now, what is the next thing you do when you do measure theory? Maybe you build general measures, but if you like probability, you just work with probability measures. And here I just sloppy identify measures with their densities since I'm thinking of a discrete space, okay? So let's think of a probability density with respect to the counting measure if you are very fancy with measure theory. Then, but specifically, there is the delta, the Dirac density, right? Or which is just 1 on a point x and 0 elsewhere, or the Dirac measure. And then, okay, maybe we'll be more precise on this. So there's a key object which gives you a sort of, oops, yeah. I just touched the cable. Also yesterday, that. Oh, somehow. Okay, it will fix it. So that if you want to transport densities or measures, of course you can think of a function, but another natural object which appears in probability is a Markov kernel. Okay, is a so-called transition kernel. We will give more details on this later on. Okay, so for the moment, if you don't know what this is, let's skip. Yeah, another basic construction that you do in probability or in measure theory is the product space. So given two sets, in this case, you take the product set, the Cartesian product, and if you have a function in particular, you can do the partial summation over one slice. So for example, you fix y and you sum over x, or then you can also sum over all the possible pairs of x and y's, and you get the double sum, right? Okay, now these are not theorems if E and F are just finite sets, okay? These are just trivialities. Another important thing is that if you apply this construction to the density, you get the marginal densities, right? So if you have a joint probability density, you fix x in this case, and you sum over y's over x, right? And you get the marginal distribution. Now, instead, finally, I just listed here two important quantities related to probability densities, which are the Shannon entropy. Actually, this is with a natural basis, but anyways, it's minus the sum. So it's a sort of expectation value of the logarithm of the probability density. Now, the minus the log of the probability density is this log of 1 over p, because you have a minus. So essentially, the smaller is the probability, this log will be larger, but not so much because I'm taking the log essentially. So, and this gives you an idea of the information content. So how much random this probability density is. So how much uncertainty we have in P. Okay, this is a basic quantity in information theory. And then you can also turn it into in a sort of relative quantity, because it's just S of P random with respect to what? How much uncertainty we have with respect to what? You can turn it into a sort of a non-symmetric distance, but it's called the Kullback-Leibler divergence between P and Q, which is just this quantity here. You have the sum over all the values of the probability, and then you do not just the log of P, but the log of Px divided by Qx. Q is usually a reference measure, and P is what you are trying to study. But it may be also reversed. Okay, in some applications you focus more on Q and you keep fixed P. Okay. Anyway, these are basic quantities, just to show you a bit what are the corresponding quantities in the quantum case. Okay, because we have more or less a full correspondence. There may be choices, okay, but more or less these objects are fixed. So what is the analog of a probability density? So we told you that a function has its analog as an operator. So what we have here is that if you think of a density as a special function, you have a special kind of operator, which we write with rho typically, which is a so-called state operator or quantum state, if you're just a physicist. So a state operator over the quantum system described by H. What is this operator? This operator must be self-adjoint, because you want the density, the probability to be real valued, and also non-negative, because probabilities are non-negative, and the sum of the eigenvalues with multiplicities, so the trace is 1. Okay? So these are trace 1 self-adjoint non-negative operators. Now, states can be defined also in a very abstract way. You don't need to enter this formalism. If you work more into free probabilities, you may say, wow, but this is a very special case. But somehow, usually in the quantum setting, you prefer to work directly with state operators, which become matrices once you pick a basis. Okay, also called the density matrices. Now, among these these states, which are general, if you want, they correspond to general probabilities. There are special ones which correspond to the Dirac deltas at a point. And as I told you, points correspond to elements in the Hilbert space. So you just take the operator, which is the orthogonal projection on psi, where psi has a unit norm. Okay, otherwise it is in this case so this is just the operator, so which takes any phi on H and gives you the scalar product between psi and phi. So it's a complex number times psi. Okay. So you are projecting geometrically on the line given by psi. And sometimes you just do a correspondence. So you just identify this state operator with the state vector, which is also called the wave function. Okay, something that appeared also yesterday. But be careful that once you have this, well, it is well known, right? If you have a wave function is, if you want, unique up to a scalar complex number with modulus 1. So you have a global phase in physical terms, while this state operator is well defined. Okay, because if you multiply psi by a scalar a complex number with modulus 1, this will not affect the orthogonal projection because you're projecting on the same line, okay, on the same ray. Okay, now what is the counterpart of Markov operators? There is a well-defined notion of quantum channels, these are called, or completely preserving, completely positive trace preserving operators. Okay, but we will do a bit more on this a bit later. Now let's go to the product instead. So if you have two sets, you would like to do the product of two sets, it's a set. If you take two vector spaces, what is the reasonable notion of product is a tensor product. Now these are Hilbert spaces, so you want also to give a Hilbert structure on the tensor product. Okay, so now you know the tensor product you can define it in many ways. The important thing is that it is generated by elementary tensor products, like let's call them phi tensor product psi, right? If you pick an element in H and one in K, you have this, if you want, these elementary tensor product of objects which belong to the tensor product. Now, on this elementary, the span of these generates H and K, right? Depends now if these are finite or infinite dimensions. But on these, you can easily define a scalar product by simply taking, if you have two objects of this kind, you take the respective scalar products, okay? And then you extend by linearity. Now, so you have a natural notion of product, and at this point, remember, we have a natural notion of trace, which corresponds to sum of an operator, and but maybe before I move to the trace, I need to tell you that we also have a natural notion of product of two operators, which in terms of matrices is simply the Kronecker product, right? So we have an operator on the tensor product that into itself, for example, can be, not necessary, of the form B tensor C, which B is an operator from H into itself and HC from K into itself, which acts trivially on elements of this kind, and then it's extended by linearity. Of course, not all the operators are of this kind, but these are sort of basic. This corresponds, for example, to functions of two variables that are expressed as a product of a sum of a product of a function of one variable times a function of another variable. Okay, these are not all the functions of two variables, but it's a useful set. Now, on these operators, and more generally on all linear operators on H tensor K into itself, you can make sense of a partial summation over, for example, the system H. Okay, this is called the partial trace. I will give you a bit better the definition later on. But just to tell you, it's a corresponding object to the partial sum. And this is done in such a way that, for example, once you do the partial trace, you have an operator on K. If you trace again, you will just do the total trace. Okay, these are just corresponding to this Fubini type identity. Now, this is relevant for us because once you have a quantum state, you do the partial trace, for example, over K. This is a special case of if it's a joint quantum state on the two systems, H and K. By doing the partial trace, you recover what is the marginal distribution. Okay, this is called also the reduced density or reduced state on H. If you trace out K, you just look at the marginal on H.
Dario,
yes.
I mean, I think it's more or less the same, but the second trace after the trace of H should be just trace, right?
Yeah, yes, right. I'm just emphasizing here that first you trace out the system H, you get an operator on K, and then you apply the trace, simple trace operator, not the partial trace, you're correct. I'm just saying that here you just do the total trace of what is an operator on K. I'm just writing as trace K, just as you write here summation over Y, summation over X, just to remember that you're doing. But anyway, you're right. This is just a full trace operation. Now what about the entropy and relative entropy? This will pop up in the last tutorial, but just to tell you a bit about operator calculus. So if you have a reasonable function defined, for example, on states, right? You have summation of P of X logarithm of P of X. Now, how can you say quantize this object if you want to do a quantum analog? Well, the first thing is that you say these are the values, P of X are just the values. So I just replace this P of X log of P of X with what? If the matrix, if the operator is diagonal, I just do apply this on the diagonal. If it's not diagonal, I use the spectral theorem if you want to diagonalize. And then the summation, as I told you, is a trace. Now, what you realize is that you don't need really to diagonalize, essentially. To define an object like a trace of a function of rho, right? You may say, okay, I first diagonalize rho, I apply f on the diagonal, and I do the trace. But now the trace, the point is that if you have a unitary, which the change of coordinates that brings you into the diagonal matrix representing rho, commutes, if you want, with the function, and also leaves the trace unchanged. So essentially, you get a basis of what you have a glimpse here of what is operator calculus. Okay, if you have a function of an operator and you want to trace it out, you can define it easily by simply writing the function applied to the state, which means operationally that you put yourself into the diagonal in a basis where everything is diagonal. You apply the function to the diagonal elements, 0 elsewhere, and then you trace out. Okay. This happens as well here. One needs to be a bit more careful about the relative entropy, because now you have two operators, rho and sigma. Not necessarily they will be diagonal in the same basis, okay? But still you can give a meaning to this, okay? This is the definition, one definition of relative entropy, okay? Because now it becomes a bit more tricky. There might be other possibilities, okay? So this is a bit similar to what happened in free probability, right? As long as you have a single one, yeah.
I just want to comment on the free probability. Yeah, I think one of the main differences, though, is that the trace is usually taken to be more abstract, and I think there's reasons for that, like the trace class operators, where it's defined.
That's true as well, right? In free probability, you directly work in a much more abstract setting, but also the trace, you are more focused into taking traces, where here you have a sort of a state which represents so somehow in free probability, the way I think is that you have a sort of very big space where you have a uniform probability, which is this trace, and then you have all the random variables, which are the x and y's. Maybe this is my But here in quantum, you fix a state. Usually the physical information is encoded in the state, which is not a multiple of the identity. So you still have a you still okay. I need also to change the slides quite often. Otherwise, but we can discuss a bit later now, because I'm not really an expert in free probability. Just my point of view may be very biased, because I think in terms of classical random variables.
Maybe you can just add one comment. So what relative entropy, if you first see it, you say this is an absolutely awful definition because you're doing this minus log sigma.
Yeah.
It's absolutely awfully useful. And all these phenomenal algebra questions have been clarified by the work of Araki in the 70s.
Exactly.
So he knew how to circumvert all these minus log sigma.
Yes.
So that if you want to know, I can tell you where to read it, and it's 40 years old. Right?
Yes. I mean, these are classical objects. I'm not.
But even type 3, I mean, the worst algebras you can think of, everything there in terms of relative entropy is understood.
Yeah. No, but I'm familiar. I mean, the theory around these objects, both from a more mathematical and more quantum information theory, were very well developed. I was just showing out some sort of definition to give an example, and also because it will pop up at the very end.
On more historical note, it's interesting that S of rho precedes.
Exactly. This is also called the von Neumann entropy, okay, right? And the von Neumann, came after Boltzmann for sure, because I guess the idea of taking entropy in the sense of log, but Shannon came after. I think it was really influenced by von Neumann.
Yeah, right? Von Neumann actually, I think if you look at his paper, he was influenced by Gibbs in writing this formula.
Yeah, also Gibbs, right? Well, okay, but this ends a bit this table, but I want to focus a bit more on the operations of trace and partial trace, because also they will pop up, I think, in Augusto's tutorial, so I can explain them before Augusto does. So, as I told you, once you have a state operator, a state should be thought in general as a state operator, okay? Not necessarily a pure state, so a wave function or a state function. So a state operator, you can pick a basis, say that you have everything in finite dimensions, okay? And then you write, well, let's say that this is an orthonormal basis, so a Hilbert basis of H. And then you have a density matrix, which is just your matrix which represents the operator. Now, what happens if the operator is self-adjoint, the matrix will be Hermitian and positive semi-definite if the operator is a positive semi-definite. So we have really a matrix, a state matrix, density matrix, sorry. What happens on the diagonals? Since the trace is 1 and this is positive semi-definite, on the diagonal you will really see a classical probability density. So you can really think of a quantum state like this matrix, where on the diagonal you have a sort of classical probability, and on the off-diagonal terms you have these strange objects, which in general will be also complex. Okay, so this may be a point of view if you want more practical things. But the point is that by the spectral theorem, you can always find a good basis so that it becomes a diagonal. But the point, what is the catch in quantum, in these non-commutative settings, that the basis will depend on pi. So essentially, you can find the right point of view and see a classical object, which no off-diagonal terms, so just a classical probability density. But this point of view will change and non-trivially depending on the state that you have. Okay, this is maybe one way to see that things can become more different. Now let's see a bit more on the technical side. What is this partial trace that I told you? So you can also see the partial trace in terms of basis, and maybe this is practical definition, maybe not very elegant, but useful if you want to have a maybe if you are practical by taking these reduced density matrices and stuff that were also yesterday mentioned. So you take, say, you're in a product space. It's known that if you take an orthonormal basis on 1 and orthonormal basis on 2, you have a common orthonormal basis based by the elementary tensor products. And now you can write this big density matrix. Okay, write it with 4 indices, but these are just pairs of indices on one and the other basis. So explicitly, it's this, okay? So you have this is one basis element. This is the dual, corresponding dual for these other 2 indices. And then you have these numbers, okay? Complex numbers in general. So what is the partial trace over H? Well, over H is the first system. It means I just do the summation. I do a contraction, if you want, of the indices over the first components. So I put I equal K, and I do a summation. And I just kill all the first terms here. So what I'm left with is an operator on the second. Okay, this is really, if you want, the operative definition of partial trace. Not so nice because it seems that it depends on the basis, right? But you can show that this operation does not depend on the choice of the basis. And similarly, if you want to trace out K, you do the same thing on the second coordinates, if you want, right? You do summation over J, you put J equal L, you do the summation, and you are left with an operator on K. Okay, yes.
So the same as integrating, so if you have an operator to T, let's say, to which you want to apply a partial trace with respect to H.
Yeah.
It's the same as integrating over the unitary group of K.
Yeah, averaging. You mean yes? It can be thought that yes, this summation. You can think of this in fact, right? To average out the system over the H, right? And now this summation is it's just a final summation, but it can be thought also as a Hardy integral type of operation. Yeah.
Can I please go back to the previous slide? So, like here you mentioned that, like in this second point, the diagonal pi I is a classical probability density.
Yeah.
But like, so to me, it seems there should be a probability density. So I know that the trace of a diagonal is still 1. So it's like the condition for being a density matrix.
Yeah.
But like, is it like just some way? Because like when we diagonalize,
yeah,
we get the eigenvalues that still sum to 1. So and it actually is a different probability.
Right. Yeah. Be careful. Of course, if you fix any basis on the diagonal, you will see some elements which sum up to 1. These are non-negative, but they will not be the spectrum, of course. So some of the right basis is sort of this the eigenbasis. But if you want to think, say, I have this density matrix, what does it look like? It means that, in a sense. Well, given also by the measurement postulate, if you want, the probability of if I am in a state, in a pure state, so if I observe, if I do build up an observable made up of this projection, I will see psi j with probability pi jj. Okay, these are classical probabilities corresponding to some observable, some operation you can do, but these are not pi I. Of course, it's a different thing. Okay, no. So the off-diagonal elements count a lot. I mean,
Yeah, it's just like it's kind of weird because like we kind of fix the operator pi that it should correspond, like if its diagonal should correspond to some one unique probability density, but
yeah, but
Here's that one that you get in the basis of its eigenvalues.
right.
It comes with a special basis of its eigenvalues.
Depends. If you have a really preference for some basis, you would like to think in this term. I have this classical probability with some strange correlations outside, which are complex things. On the other side, if you're, say, I focus on the state, I know there is a good basis for the state, and this will be the eigenbasis. But it's just a point of view, it's just a way to think of these things. I don't know. Yeah.
I'm pretty sure this partial trace is also the same as the adjoint of the canonical embedding from like.
Yeah. Okay. No, there are many better definitions of partial trace. Okay, this is just a way to show one concrete definition. Otherwise, it becomes just an abstract object. While it's really linked to the reduced density matrix that was shown yesterday, or reduced state. I don't remember the name that was given yesterday. Talk by Kasia. Okay, some exercises maybe we can skip, but okay, because I just recycling some old. Slides, but one important thing is this one. You can build several kinds of superpositions of quantum states, okay? So also probabilities. If you have a classical probability, you say, I toss a coin with probability P, I will select one experiment. With the probability Y minus P, I will select another experiment. This is a thing you can do. But in the quantum setting, you can also do a different kind of superposition, okay? If you want a superposition in terms of wave functions, or state functions. So what you do, you can still take P. If you take two orthogonal vectors, okay, psi1 and psi0, then you can define this new vector, okay? You can call it a superposition of the two with, I don't know, with amplitude P. I don't know if this is a name, but anyway, you can define this object here, okay? So the question is just a simple exercise. Are they the same? No, because this corresponds to a matrix in general with rank 2, and this instead is a vector. So if you build the state operator, it will have a rank 1. Okay, these are two different kinds of superpositions, and the useful one from a quantum point of view are these one. Okay, these are more like classical superpositions. You do a random experiment, and with some probability you select. Given the outcome, you do something on the system. Okay, you put the system in state this or state say 0. Well, this is a more complicated thing, and in fact, for example, being pure, its entropy is 0. Okay, so the Shannon entropy. So the typical kind of these states are, for example, the Bell states. So these are all orthonormal. Yes, it's written here. Okay, vectors. You do this kind of uniform superposition in the quantum sense of these elementary tensor products. And what happens is that these are pure states, but if you compute the marginal distributions, the reduced density operators, they will be non-pure, okay? Which is something that you say, okay, it happens, but classically it's quite surprising, because if you think of a pure state in terms of a Dirac delta, so if you have a random variable which has a law which is a Dirac delta, if you look at the marginals, even if this random variable takes values in a product space, their marginals will be Dirac deltas. So from a global point of view, this is a sort of Dirac delta distribution, but if you look locally on the system H, system K, so on the reduced systems, you see something which is random, okay? So this is an emergence of a new phenomenon, which is entanglement, okay? This is an example of entangled state. Yeah.
Could you remind me what S of H is, and possibly how you would?
Yeah, sorry, S was the Shannon entropy definition. There are many, von Neumann, sorry, von Neumann.
The Hilbert space, not of the...
I'm sorry, no, these are two different slides. S is a state, sorry. S of H is a state operator. So it's a self-adjoint operator from H into itself, non-negative, so that the trace of rho of the operator is 1. Okay.
Just having the properties that were like shown in that first comparison slide.
Okay, maybe I didn't write a slide with exactly the definition, but it's what corresponds to the classical notion of probability density, okay? So quantum state. Should I write it? So it's something that you can, if you think in terms of a matrix, if you pick a basis, it's like this. So you have a matrix which is Hermitian, positive semi-definite, and trace 1. Okay.
So one more. So the state in S is ensemble or pure state? Or both?
Yeah, you can also think. Yeah, exactly. Let's go back to this. Nowadays we have a notion of classical superposition, if you want. If you have a state pi, right, a quantum state, you can always put it in this form. So now you recognize this is a classical probability. What does it mean? It means that with some probability pi I. So for example, you have an extra experiment which gives you outcome I with probability pi I. And then if the outcome is I, you prepare your system is prepared, if you want, on this pure state phi I. So you can think of this as a classical superposition of these pure states. Yes, you can also think of a quantum state as an ensemble. Yes, as an ensemble. This is the physical notion term, but if you want, it's a classical mixture of pure states. Okay, you can also you have to be careful with this, because this is, if you want, is a canonical way thanks to the spectral theorem. But if you have a more general, if these phi I are not orthogonal, but they still, if you do still a summation over it may be also infinite if you want a family of phi i's, such that the pi's sum to 1, this will also give you an ensemble and a representation of a state. Okay. But this, if you want, is a canonical way using the spectral theorem. Okay. Yeah, there are many ways to think of quantum states, and all of them may be useful. It's difficult to get a single. Mathematically, we all agree on what they are, right? But every point of view may have pros and cons. So let's move to, for example, a concrete example based on qubits systems. So what do I mean? I mean that we look for a quantum analog of this set here, which is simply the hypercube, discrete hypercube in dimension n, right? So what do I mean? I mean that for every pair 0, 1, I replace it with a two-dimensional complex Hilbert space, which is just C2. And then I do the product n times, which means I take the tensor product of C2 with itself n times. So instead of doing these elementary tensor products only twice, you can do it n times. And now if you have a standard basis on C2, which is just the basis you just denoted with quantum notation, is simply 0 and 1, right? 0, if you want, is the vector 0, and 1 is the vector 0, 1, okay, in C2, right? You can do the tensor product of these elements, and for each string, bit string of length n, so for each string you will have an element in the tensor product. And of course, you can check, given the definition of scalar product, since you need to take the scalar product of the components, if you have two different strings, they will be orthogonal. And the dimension matches, so this is a basis, if you want, it's called the computational basis of the system with n qubits. Okay, bits because these are two, okay, 0, 1. Now, of course, you should not be, so these are bits, though these are two, but the pure states are many more, even already when n equals 1, right? We saw yesterday this picture, because you have all the superpositions, so you have all the unit, how does it go? Okay. So the pure states are all, can be easily parameterized. I'm not doing the explicit parameterization over a sphere, the so-called block sphere, but also there are the mixed states, sometimes are also called this way. The general states which are not necessarily pure are also inside the block ball, okay? Now for n equal 2, this is an example of the basis. Okay, so what is the dimension of this? Every time you take a product, you need to multiply the dimensions. So this is 2 times 2 n times, so this is 2 to the power n, okay? So the dimension grows exponentially, as the number of strings grows as well exponentially, okay? So the dimension reflects a bit the number of elements that you have in the classical case. Okay, so just to recap, so now since if you have two Qn states, sigma and rho over the system of this, so maybe the bracket here, there could be another bracket would be better. So over n qubits, each of these states is represented by a big matrix, say 2 to the n times 2 to the n, and these are still complex Hermitian positive semi-definite with unit trace matrices. So, but you see, they grow very easily, right? As yesterday, there was this example of 2 electrons, 3 electrons. If you're just focusing on qubits, which are even simpler than particles with a position in space, a velocity, and maybe a spin, right? So essentially, here we're just looking at the spins. So they still grow very easily, very, very much. Now, what are pure states? Pure states are rank 1 matrices, and they correspond to some unit norm vectors, but be careful, they do not necessarily correspond to actual strings, okay? Like you can do any superposition between 2 strings, different strings. Now, what are instead classical probabilities? How do they match with this setting? Well, classical probabilities, if you have this preference for the computational basis, correspond to matrices which are diagonal in the computational basis. Okay, this may be a choice. Is not canonical, but it's a good way to embed the classical probabilities into systems of n qubits. Now, quantum computing. Why? Okay, 1 second. Yeah. So maybe I mentioned a bit quantum computing. This is not the focus of our tutorial, but since I'm mentioning n qubits, you may say, okay, what are the operations we can do with these qubits if they correspond to quantum bits? Well, the point is that the natural operations are unitary operations that I will give you a bit more about the axioms of quantum mechanics, but typically in computing you have a simple restricted set of operations which apply only to a single or a pair, or maybe you can see operations which apply to 3 qubits at once. Okay, so you need to select on this very huge space just 2 qubits. In theory, you should be able to select any 2 qubits, and then you apply maybe, well, if it's a single qubit, you can apply simple operations like this, Pauli X, or this is called the Hadamard, but these are just unitary matrices, which corresponds to unitary operations. But then you have more complicated operations, or into 3 or so. So just a simple exercise, but show that these are actually unitary operations. But why unitary operations and not more general operations? Because the postulates of quantum mechanics prescribe essentially that you can do 2 things, okay, in a quantum system. So if the system is closed, in the sense it's isolated, the postulates tells you that it will evolve if there is now here I'm writing this as A, but because I don't want to use another time H. So there will be a Hamiltonian of the system, and if the system is closed, it will evolve according to Schrödinger equations, okay? Now the resulting evolution, now here, the resulting evolution will be a unitary transformation, okay? Now if you want to bring states into states, if you prescribe that the evolution is linear, it will be a unitary evolution. Okay, so this is one way to evolve a system. So when you act with these qubits, with these elementary unitaries, you are thinking, well, there will be maybe some physical evolution given some some Hamiltonian, which will take me after some time from the initial state to the state where I applied this unitary. Okay, this is the point of view. But then there's also another postulate which tells you that if you measure the system, instead if you open the box and you see what's happening in the system, you can describe the measurement operation in terms of an orthonormal basis. In some sense, this corresponds to your measurement system. So you sort of fix an orthonormal basis, which corresponds of the things you're measuring. And now if the state is pure, at least, the outcome, you will see outcome V, the value V of your measurement, with probability given by this postulate, which is just Born's rule. What I'm saying here is a bit, yeah, okay, let's keep it this way, okay? So this is just the scalar product between your state vector psi, because we are in a pure state, and the vector phi v, which corresponds to the value v. So this is a probabilistic rule. Why this is really an evolution which is, so you have this unitary operator which brings you this state vector to another vector. This is a sort of a probabilistic, is a mixed rule, is a slightly different in nature, because you see that you can measure, you do your measurement, and then you will see value v with some probability given by this Born rule. you can check that these sum up to 1. These are standard probabilities between 0 and 1, they sum up to 1. And now after the measurement, okay, now we have to be careful, because if you see, the rule is like this. If you know that the actual, if you observe a value of V, the system will collapse to the projection essentially on phi V, okay? Now before, if you want knowing what is V, you will have a mixed state. You will still have a collapse of the state vector, possibly in a mixture of states. So you will have this new state here. So if you want, this is a continuous evolution, and this is instead like of a jump, is say a sudden change and update of the state function. So they have a slightly different nature, and it's quite interesting that you may think maybe I can combine these two. So can I do something which is in between evolution and measurement? Yeah.
Part two. So I always thought that if you take a measurement, that in the end of the day you are in a specific vector state, so but not as a superposition.
Yeah, no, it depends. So if you want, there is an extra. I try to be careful here because I want to allow also these channels, right? The point is that if you know that you performed the measurement, you will be in this state, okay? Now, if you observe V, you will be exactly P. So if you do the actual measurement, you observe V, you can say, I will project on the eigenspace, okay? So I'm just splitting, if you beat this rule into two sub-rules, if you want. You know that before doing the measurement, you will see probability V with this. The probability of observing V will be this. If you want, after you observe, it's like tossing a coin. Say, I choose to toss the coin. No, sorry, let's do it with more. I toss a dice, right? So if I choose to toss the dice, I know that I will see probability with probability 1/6, say, each of the 6 outcomes. Now you may say, okay, what happens if somebody tells me that they have tossed the dice? Well, I know that the outcome will be 1 into 6 with these probabilities. So and then if I look at the outcome, I will have exactly one of these, and it will be that specific. If you want, it's a similar situation. If somebody tells you, okay, I've measured the system with this observable, with this basis, I can tell you yes. So the outcome will be this with these probabilities. And if you tell me that you performed the measurement, I can tell you that you will be in this state. Of course, if you haven't told me which one of the V you have observed, I can tell you that you are here, not in the psi V. Okay. If you want, you can split a bit these two steps. I mean, it's quite of a yes.
So one has to say that the fact that all the outcomes are diagonal in this basis phi V is dramatic. Dramatic because that is what is called an entanglement breaking operation. So if you have entanglement, whatever that is before, now it's gone. So there is one and two.
I'm not saying that because in principle, no, entanglement is a property of a joint system. Yes. So here, I'm not saying what kind of measurement I'm doing. In principle, mathematically, any orthonormal basis is allowed. For example, in principle, at least, you could say, I do a measurement which creates some entangled state. You could do also this, right? I mean,
but for every psi, you end up in this diagonal structure.
Yeah, so in general...
That is extreme, right?
Yeah, it's an extreme. These are two extremes, and this is what I want to emphasize. Somehow you can find an interpolation between the two, and this is what we're going to do now. Okay.
So can I just ask, I'm more lost. So when you say that you did a measurement, but you didn't look at the actual value that you measured,
yes,
you have done nothing, right?
No. Say that I'm in a room and
the measurement disturbs the system.
Yes, you're saying if you know that you perform the measurement, say that your friend is in a room, is in the lab, and he tells you, okay, now I perform in the measurement. Depends the way you interpret the thing, but as long as when you perform the measurement, you are collapsing you are doing this dramatic change. And but even if the friend haven't told you what was the outcome from the quantum mechanics perspective, you've changed the state. It's not like so.
That's what I understand. I mean, if your state before was given by some density, you've just written this density in this particular orthonormal basis. You haven't changed that.
No. This is a different
this
thing.
is a
This is a
trace.
different
It's
thing.
unfortunate how you wrote it, because so before measurement, the state is given in the last line. The last
The
line.
state is
the last.
psi. So before,
Okay.
Yeah, so it's before the measurement. Then you measure the measurement makes the system collapse to one of these.
no, before is psi.
So
Sorry.
I'm talking about the last piece of the last sentence.
After the measurement system is in state.
Because it suggests that this is
right.
after
Yes.
measurement, but this is before measurement.
It lives in this.
Okay, no, that's okay. Let's look just at the mathematics. These are two extremes. It depends the way you interpret this thing. Okay, I'm not saying that before this is the way you think about this postulate is a bit tricky. Let's put it this way. Okay, that's.
Sorry, I'm a bit confused. So, are we talking about, so we are fixing the basis phi v, right?
Yeah, fixing a
Phi v is the
measurement is
basis of
sort of.
h.
Yeah.
And we're taking another element psi of h.
Yes,
And
which
we
is,
know that like you can write it inside the basis phi v. So and the weights or like and the coefficients of the basis will be determined by this phi v. So maybe in the last line you actually mean not, because the last line is an operator, is not an element of a Hilbert space.
yeah, this is a mixed state. It's a state operator. This one is a state operator. What I'm saying is that if you choose, okay,
Is it like
you don't like it? Okay, stop.
No, is this is supposed to be the psi, the cat psi, bra
this is
psi
so-
is equal to this phi v, or no? Because we start like you're saying that we are starting with
we're starting
psi
with a
that is
pure.
in H.
Yes, okay. Okay,
So
I'm a bit
it's a
sloppy
wave
here.
function
Yes,
of
as I
the
told you,
state.
I'm identifying. So if you have a pure state, it's quite common to identify the pure state with the state vector. Like yesterday, there was, for example, just psi, the wave function. So even if you start with a pure state, you choose to do a measurement. If you choose any basis, you will do something very disruptive, say, and you will end up. You can say, if I don't want to have the outcome, and I'm writing this way because I want to introduce what is in the next slide, which is the channels, okay? But if you put yourself in the point of view of somebody who just want to say, okay, the measurement has happened, I don't care about the outcome, you can represent what happens after the outcome like this. Before it was a pure state. After the outcome, without caring, if you want, what is the actual value, you will be like this. Of course, if you know that the outcome as V, you will be precisely in the pure state phi v. Okay, put it in this way. Okay.
So my question was more like, is this is a wave function or is a state that you identify with this wave function psi?
Which one? On top?
Yes. So in here,
on top,
this
when I
is
say
like a
if
wave
there's-
function psi, and if we're talking about states, it should be like psi.
Okay, now I show you what is the general. Okay, these two I just showing the postulates in the case of pure states. So which tells you that even if you start with a pure state, if you don't care about the outcome of the measurement, but you just care of the fact that the system has undergone the measurement. If you want the same point of view, if you're an information engineering, and you know there will be an actual message transmitted through a system, but typically you say, well, I don't care what will be the message, I just say it's a random variable. But of course, people who do the message, of course, they care about the specific message. So what I'm saying here is that if you don't care very much about what is the outcome, you naturally end up with a mixed state, with a mixture of states. Okay.
So is it fair to say that all what the measurement is basically taking some density matrix, which may have come from a pure state, but some density matrix in the basis phi v, and then getting rid of everything but the diagonal?
Yeah, exactly. You can think of this to this point.
And if you do it for densimeter, this inner product square becomes a trace, and then it's actually linear.
Okay.
Right.
Okay, let me go to the next slide. Sorry. So these were the postulates in the case of pure. So maybe they're more confusing than I thought. But typically they're written just for pure states. Now you can say, okay, now what happens if I have a mixed state, right? An ensemble of pure. So you can say simply, I just say these are linear rules. I just apply to each of them, each of these psi. Okay. So if you have a unitary evolution, UT, it turns out that you need to essentially take a conjugation with the UT. Okay. On the left with the UT, on the right with UT dagger. Okay. And for the measurement, as you said, right, you write it in the basis of phi v, you select the diagonal things, and then you do the projection. Okay, this is again because you don't care about the actual value v that you will be observed. Okay, now can we interpolate between these two? Is there something in between? Should I really only close the system or let it open it and disrupt everything? See, well, there is both transformations are linear, map states into states. So you may think, okay, maybe just a linear transformation that maps states into states is something good that can be physically done. And the point is that it's not exactly like this. I mean, you can single out a more nice class, which is called that of quantum channels or completely positive trace-preserving maps. So if you have a quantum system H, and you look at a linear map, which maps, when restricted to states, maps states into states. This is linear even if I write it with a bracket rho, okay? Now, it's called a quantum channel if it has a slightly stronger property, which is that of complete positivity. What do I mean? It's something which is not maybe immediate from a classical point of view. The point is your system H typically is a subsystem of a larger system. You can think is a particle in the lab, which is also inside of the lab, inside of Los Angeles, inside of the universe, and so on. So if I think of my system inside as part of a larger subsystem, so I say I tensor with another subsystem K, which you can think of an environment, and if I act, I take a joint system, a joint state on H tensor K, and I act with phi on H, and I do nothing, so I tensor with the identity on K, I want still that this map, this is a physical operation, should map states into states. So you say, but this is trivial because you are doing nothing on K. The point is that there are states, like for example Bell states, which are entangled. So when you consider a joint system, you have to take into account this possible entanglement, these non-classical states like the Bell states, okay? So this is just an extra condition that we add, but which is quite natural and makes the mathematics quite satisfying, I would say. So we require the map to be linear, to be completely positive in this sense. In particular, this means that it maps positive semi-definite operators into positive semi-definite operators, and also trace preserving because you want to preserve the total mass, the total probability. Yes, so a simple exercise, convince yourself that, okay, it's maybe not so simple given this short tutorial, but unitary evolutions and these measurements, as I told you in the slide before, actually define quantum channels, okay? So these are a more general class, and there are many ways to think of quantum channels, and the most two important ones are, except for this abstract definition, are more practical in nature. There is the so-called Krauss representation, which tells you that if you have a family of linear operators, let's call them BK, say that the channel is from H to H, so these are linear operators from H into H, such that they satisfy this, say, is a sort of resolution of the identity. So if you sum up these are the non-commutative analogs of the modulus squared, right, of this BK. These are not necessarily self-adjoint, the BK, right? So you do this sum over K of this BK adjoint times BK. They must be the identity. Then you can build a channel in this way. So if you have a state rho, you will do the summation over K of BK rho BK dagger. So you can check that the trace of phi rho, given this condition, will be 1, if rho has trace 1, but also that it will be positive preserving, and also actually it's completely positive. And interesting, how do we interpret this? Essentially, you are saying something like, but it's very, very imprecise, that this BK sort of a Markov kernel. You're saying if event K happens, I'm applying this BK. You can think of in this term, but it's really, say, maybe far from being precise. Another useful representation, but this is practical. You know that these are maps of this kind. And actually, all the channels are of this kind, okay? This is important, not only that these are examples. And similarly, you can also define a channel in this Stein spring dilation description. So you say, if I have a channel, I can build an extra quantum system K, a sort of environment, and a state which you can take, for example, a pure state on K, just a pure state, okay? This is just a state. I write 0, but it's a state, okay? It's a vector of norm 1. And then there's a huge unitary on the joint system H tensor K, so that actually the channel applied to rho is actually the result of this operation. So you take rho on system H, you do the tensor product with the pure state on this, say, if you want, this is a pure state on the system, K, is something that is auxiliary. You do the evolution with this U unitary on the joint system. So this is a sort of closed system evolution. And then you do the trace over K. So you forget about K, you take just the marginal, and you look at the marginal of H. Okay? This is the Stein-Spring representation of a quantum channel. Actually, you can always take K to be a copy, an independent copy, a different copy of H. So if H has dimension D, you don't need to do, if you want a maximization over an abstract set of quantum systems K, but you just need to take a system of dimension D. As much as the dimension, the original dimension, okay? Exercise what? Describe, yeah?
So if you allow for the state of the other decay space to be not pure, do you get less, like you don't get any help on the dimensions of that space?
I'm not sure. You're right. Typically you do it with pure, you say if you allow this to be non-pure, you may have a gain in the dimension.
I mean, I'm asking.
I don't know.
It's delicate.
Right.
There are other choices. We use other vectors than non-pure, and that's not totally clear what that buys you. And sometimes it's a restriction. For instance, sometimes we do this with a normalized identity, and that's too little. The class is too small.
Yeah, so you have to be careful. So surely, if this is pure, so if this is pure, I guess it's this bound is sharp. So the fact that the dimension is the same as K, it's proven, right? Sure. If it is non-pure, perhaps you can, for special channels, you can do something better. But you're right. It's not.
The correct formulation is not with a unitary, but with a partial isometry. And
yeah, okay. But let's say this is a finite dimension. Okay, it works also in infinite dimensions. So there are very interesting things.
That's the reason for this pure vector, and the partial isometry is unique, and the unitary is not. So there is some fine print about this.
I didn't say it's unique. Yes. Okay, so you can really pick copies. You can think of this K as an extra auxiliary system that, for example, for numerical, because yesterday there was an optimization over a very abstract set of algebras, right? But this, in this case, is not a very abstract object. Okay, you can take if you want as a copy. Okay. Now we have still 10 minutes. Maybe you can move to the classical optimal transport story. I hope also if you have questions on these things that we can discuss, it's quite interesting. We have also a lot of experts in our program, so feel free to ask. Okay, if this is the first time you see these things, it's better to maybe think of them a couple of hours and try to understand the basics. Now, let's move a bit back to the Monge and Kantorovich formulation. I think Augusto is going to discuss a bit more about this. So this is the same as yesterday. So just a very basic and elementary approach to optimal transport, like a combinatorial optimization problem. We need to find, remember, an optimal map that moves a source distribution to a target distribution. Now, what is the problem? If you do simulations with points and you can find this map, but you find out immediately that in general you cannot find precisely a map, because, for example, if one distribution, the 2 points are overlapping, so you have 1 point which weights 1, say, for example, another 2 points which weight 1/2. Well, from this point of view, if this is a single distribution, these are 2 distributions, a single map cannot do the thing. You will need to split the mass. So how do you split the mass? Well, you enter you allow for more general notions of maps, which are sort of Markov kernels. Now, without entering kernels, you just relax. The idea of Kantorovich is to relax the notion of a map with a coupling. Okay, what is a coupling? It's a joint probability distribution, so that if you marginalize, for example, with respect to the second, you find the source distribution. If you marginalize with respect to the first, you find the target distribution, which is the distribution of the second. Okay, and so now if you replace maps with this more general notion, you can cover these examples. So try to find explicitly what is a coupling in this case. And of course, you also improve, if you want, the nature of this optimization, because instead of optimizing over maps, which would be a sort of integer programming problem. You are relaxing and you're finding a linear optimization problem with linear constraints, okay? If you want, it's a convex optimization problem of special kind, okay? Now, okay, maybe here I can skip a bit. Augusto, maybe you're going to talk about this stuff, okay? So what I'm going to say is that this problem is very rich from a classical point of view, and you have a lot of equivalent formulations. So let me skip on this, maybe we go back. And this notion of distance gives you, if you want an extra tool with respect to classical, more simple and classical notions of distances, which are the so-called the total variation distance. So just to give you some definitions, in the classical case, if you have two probability distributions over a set X, say discrete ones, the total variation is given by this, so it's 1/2 the L2 norm of the difference. 1/2 because then it's a quantity between 0 and 1, nothing special. Another distance which is also used in statistics is the so-called Hellinger distance, which is the L2, okay, 1/2 the L2 norm squared of the square root of the probability distributions. Okay, you say, why should I care about this and not of this? Well, for example, this is more like a Riemannian style quantity because it's a sort of L2 norm, okay? So in some cases, it may be preferable to work with Hellinger instead of total variation. And this is the old friend, the relative entropy, the Kullback-Leibler divergence. All of these are the distances, possible distances between probabilities, but optimal transport gives you another, actually, families of other kinds of distances. Actually, some of these are already naturally optimal transport type distances. The total variation is the distance with respect to the trivial metric. So if you do the optimal transport cost and you pay 1 if the soil moves, whatever the length, if you move 1 meter or 1 kilometer is always 1, well, you end up with the total variation distance. Now, what is the point? These are very simple distances, simple, say, I can give you a formula, so it's simple in this sense, but they don't use any geometry of the space, okay? So if you have the Euclidean geometry, here there is no Euclidean geometry underneath in the points x and y. So while optimal transport is more adapted to this kind of geometric considerations. So if you have a special geometry, you would like to use some special adapted distance. So what happens in the quantum case? So in quantum case, it's already known and used, the quantum analogs of these classical distances. The total variation distance, usually they change a bit the name, it becomes the trace distance. So as I told you, instead of doing the L1 norm, you do the non-commutative L1 norm, as I showed, you do the trace, so this absolute value is really the square root, well, no, if you want, yeah, square root, so absolute value of A is square root of the A dagger A, okay? In this case, rho and sigma are states, so rho minus sigma is still self-adjoint, not necessarily positive, of course, but then you can do also this in terms of spectral calculus, okay? So, but you have a quantum analog of this. Also, the Hellinger distance as an analog, typically they don't use the distance, but the sort of correlation coefficient is called the fidelity, but this is the definition. And also the relative entropy, we already seen the definition in the table. So as in the classical case, these are, okay, I'm saying easy to compute or approximate compared to the quantum optimal transport kind of distances, okay? And they're quite general. In particular, they don't use anything of the geometry. How this is reflected in terms of invariances? Well, these distances or these quantities are all unitarily invariant. So which means that if you let the system evolve with a unitary u, with this distance will not change, okay? More generally, if you apply a channel, if you apply any channel, for example, if you do a measurement, the trace distance will decrease. The Hellinger distance also will decrease, which means the fidelity will increase because this is a sort of reverse of minus a distance. Also, the relative entropy will decrease. Okay, maybe this is not S but D. Sorry, this notation. So, but these are not adapted to any geometry. So the point is, can we cook up some quantum optimal transport distances? And are they useful? Maybe this is the second question that's not written here. So, but of course, you can start, and or a lot of people have done it. This is the same slide as yesterday, so I'm skipping. So you see there's a lot of attempts and pros and cons of each attempt. Now, if I want to do a classification, okay, you don't know very much about the classical transport distance, but maybe if you know, it would be interesting to say what kind of aspects are we using of the classical approach? Because maybe, as I told you, if there are many attempts, it means that there is no a single way to do this, this thing of optimal transport distance. And so there are many equivalent definitions, not only of Wasserstein 1, of sort of Wasserstein P. And classically, you have at least 3 points of view, which are all equivalent in the classical case, okay, under some minimal assumptions of the kind of the cost that you are dealing with and so on. So these are the classical Monge approach, relaxed by Kantorovich into couplings. Then there is the dual point of view from so standard duality for linear programming. Why? So maybe I should take it out. No? No, but it will work. No, it's No, I just should I take it off and on? Let's really wait. Maybe I just plug the HDMI port.
Even on
Okay, we're back. Maybe. Okay. So just to classify a bit, just to show you that people tried, as a starting point, you can say, okay, I like the Monge-Kantorovich approach. I want to transport things. Or I like the dual version. The dual version is a sort of discrepancy between the expectations with respect to rho and the expectation with respect to sigma, possibly not with respect to the same f, okay, because there's a notion of conjugate functions. And or you can like a continuous time approach where you do the continuous interpolation in time. This is the so-called Benhamou-Brenier point of view. So these are all equivalents. These are maybe non-trivial theorems in optimal transport, but classically they are more or less equivalent. And if you pick one, you can say, I like this point of view, let's see what happens in the quantum case, and people have tried it. Also, the dual point of view has been tried, and possibly the first attempt was the Kohn and Lott from non-commutative geometry, but then we also try to keep up with it in the qubit setting. And finally, there's also the approach by Massa and Karl, and I'm not aware of many other approaches from the Benhamou. Perhaps Tryphon tried as well a bit on that. So please, if you're not in this list, don't feel angry. It's just because there are so many approaches, and maybe it's difficult to list all of them. Sometimes you stop reading the literature because there are so many approaches. So just to conclude, I have 2 minutes, I think. I want to list one because I think it will be the starting point also for Augusto. You say, but this is the natural one, why should we change it? Well, this is the Goltz-Mouhot-Paul-Cagliotti approach. So the idea is this one. We have a notion of coupling, and we have 2 quantum states, rho and sigma. How can we couple them? Well, if you think in terms of Kantorovich, you say, I need a joint quantum state, which is just a joint probability distribution of the 2 copies of the system H tensor H, and I just prescribe the marginals. So if I trace 1 is the partial trace with respect to the first system, because these are both H, and trace 2 is the partial trace with respect to the second distance. So if you just look at the marginal, the reduced density operators, you just prescribe them to be rho and sigma. This is a notion of couplings. And what about a cost? Well, if a cost is a function of the 2 variables x and y, well, they should be unobservable on the joint system. Okay. Maybe as an example, you take so sort of sum of squares. You take your favorite observables. Say, for example, they should be position, momentum, but these are maybe not bounded. But you say you fix your favorite observables and you build a cost, for example, given by this sum of squares. Sorry, this is Ri tensor identity minus identity tensor Ri, not R1, of course, squared. And finally, the definition, which is quite natural, is you just minimize over all the possible couplings the integral of the cost over pi, which is replaced by, or the sum of the cost over pi, which is replaced by the trace of C pi. Okay. Now, this is a natural definition. We'll see tomorrow that there may be other definitions which are more related to this notion of couplings, of plans, of channels, because you are not actually transporting the mass in this point of view. But still, it's quite an interesting object for many applications. So as a small set of exercises, maybe I can show and share these slides. Would be nice, okay, just to put some hands in this context. Show that the inf is actually a minimum if you like these things. But for example, an important thing is to describe, notice what happens if one of the two states is pure. Well, the situation becomes very rigid in this case. You don't have many couplings. And this is a bit of a setback if you want to really transport density, not density operators, but pure states. You want to transport state vectors, this is too rigid. Okay, so this is well adapted if the state is not pure. You have a flexibility. Otherwise, it becomes a very rigid situation. And finally, this is an interesting point because there's a paper by Gauss, Muho, Paul, and Cagliotti where they show that in some cases it might be cheaper to work with this formulation with respect to the classical one. So formally, you may say, okay, you have two classical distributions and a cost which is classical, say on a qubit system. So everything is diagonal in the computational basis. It might be that, of course, in principle could be cheaper, but it can be actually cheaper. So this infimum, since you're minimizing over a larger set of couplings, you expect this to be cheaper. I think what they work out is a specific example. So it might be interesting to understand under which conditions. So is it always cheaper? Of course, if C is 0, it cannot be cheaper because if C is 0 cost, it will always be 0. So it will be interesting to understand when the quantum case is cheaper than the classical one in more general conditions. Okay, maybe I can share the slides so we can, yeah, maybe there was some bibliography, but it's hidden. I don't know how to show it. So for the moment, I'll stop here. So I can share the slides somehow. Maybe I'll put them in. We have a folder. We have a. Do we have?
You can set up a wiki. I mean, normally we set up a wiki page for the whole program.
Okay. Maybe this is good. Yeah. Okay. So if you have other questions, we can discuss later for sure.